The next talk is on modular verification of safe memory reclamation and concurrent separation logic. It's by Jaehwang Jung, who will be giving the talk, as well as Janggun Lee, Jaemin Choi, Jaewoo Kim, Sunho Park, and Jeehoon Kang.
Thank you for introduction. I'm Jaehwang Jung from KAIST. Today I'm going to talk about modular verification of safe memory reclamation in concurrent separation logic. So before we get into our work, let's warm up with an example that shows the problem of memory reclamation in non-blocking concurrency. Let's consider a linked list like this. It has the head node at location L head and data nodes at L1, L2, and L3. Suppose the first thread, T1, wants to read the data from L1, but the scheduler stops T1 and runs the second thread who wants to remove 10. In sequential programs, T2 will simply unlink L1 from the list and then free it. But in concurrent programs, this is not safe. It's not safe to free the node immediately because when T1 wakes up, it will access L1, which will be a user after free error. So to safely free L1, the reclaimer should ensure that T1 has finished accessing L1. But designing and implementing such a method is quite a difficult task. So programmers usually use libraries that encapsulate such complex synchronization in a modular interface. Header pointers and read copy updates are well-known examples. However, they are still difficult to use correctly. I myself made mistakes when I'm using them, and many experienced programmers make mistakes too. So the goal of our work is to formally verify the reclamation libraries and clients. Specifically, we want to verify many lock-free data structures that use various reclamation libraries. So there are some existing approaches for this problem, but they have some limitations. First, some of them don't support compositional verification. Specifically, we want to verify the library and client separately so that we can avoid duplicating the proofs. Second, some of them are not generally applicable. To verify complex concurrent programs, we need a powerful tool to describe their invariants and reason about them. So to overcome these limitations, we developed modular specifications for reclamation libraries in a concurrent separation logic. In the rest of this talk, I'll focus on verifying the list example using our header pointer specification. Now, let's take a look at how to use header pointer in the list example. In header pointers, each thread is given protection slots P1, P2, and so on. When thread 1 wants to use the node L1, it should pick a protection slot and call the protect function to announce that it's going to use the node. On the other hand, after thread 2 unlinks the node, it should call the retire function to schedule the reclamation of the node. At this point, L1 can't be freed because T1 is protecting it. But once every thread revokes the protection by calling the unprotect function, then the node can be freed. But actually, calling the protect function itself doesn't guarantee safety. Suppose T1 is about to protect L1, but T2 comes first and removes L1. Then L1 can be freed because the protection is not announced yet. So when T1 wakes up, even if it protects L1, it will get the user after free error. So to ensure safety, after T1 announces the protection, it should validate that the node is not already retired. In practice, this is done indirectly by checking that the node is not detached. And this works because the node is retired only after it is detached. Now let's take a look at an example of validation. If T1 is protecting L1, it should ensure that L1 is not detached. In this case, the head is still pointing to L1, which means that L1 is not detached, so the protection is validated. On the other hand, if the head doesn't point to L1, then L1 is maybe detached, so it may be retired. So the validation fails, and T1 needs to restart the operation. But validation can be difficult when traversing the list. For example, T1 wants to proceed to L2, so it's going to protect L2 with slot P2. But T2 comes first and removes L1 and L2. In this case, L2 can be freed immediately, and now T1 protects L2 and wants to validate it. But this would require checking all the links from the head, and if we traverse deep into the list, this will be very costly. So we need some additional mechanism for efficient validation. A solution is to give a warning before unlinking. When you want to remove some nodes, then we should first mark those nodes. Typically, this is implemented by setting the least significant bit of the link pointer. After that, the remover can unlink the nodes. On the other hand, the traversing thread can use this mark for validation. After protecting a node, we should check the link we followed is still intact. And if still intact, so if L1 is not marked, then we know that L1 is not detached. Oops. And if L1 still points to L2, then transitively, L2 is not detached either. So the protection is validated. But if L1 is marked, then L1 might have been detached, which implies that L2 might have been detached too. So the validation fails, and the traversal has to restart from the beginning. So that's how hazard pointer is used in the list. Now, to verify the list compositionally, we'll give a separation logic specification for the retire function, protection function, and validation. But let's try a naive approach and see what's wrong with that. And while doing so, let's also have a quick recap on concurrent separation logic. In this slide, the bottom area describes what happens in the separation logic proof. In the proof, we have an invariant. And in concurrent separation logic, invariant is the main tool for describing the shared state. In our example, the invariant says that there is a linked list starting from L head. In this moment, the invariant contains the bunch of points to assertions for the nodes. And points to assertion of a node tells us the value in the memory block, and it represents the permission to read, write, and free the node. Now, suppose T2 removes L1 from the list. Then in the proof, we'll take L1's points 2 out of the invariant. And when L1 is retired, you'll pass the points 2 as the precondition for retire function. But this proof doesn't work because this is a concurrent program. For example, T1 could have protected and validated L1 just before it was removed. In that case, the remover shouldn't take the points 2 out of the invariant because T1, thread 1, needs it for accessing L1. But at the same time, the remover wants to take it for retiring L1. To resolve this dilemma, we need separate permissions for accessing and retiring. So first, for retiring, we introduce the managed pointer predicate. In the invariant, the points to assertions for nodes are replaced with the managed pointer assertion, and it represents the fact that the points to of the node is managed by hazard pointers. When a node is detached, we can take the managed assertion out of the invariant, and when the node is retired, we pass the managed assertion as the precondition of the retire function. In this sense, the managed pointer assertion represents the unique permission to retire the node. For accessing the node, we introduce the protected pointer predicate. At the beginning, the thread starts with the HP slot assertion for each protection slot. And when thread 1 calls protect function, we update the value of the slot. But note that the contents of the invariant may have changed while protecting because someone could have modified the list concurrently. Only after T1 checks that the head still points to L1, we can know that the invariant still contains L1's managed assertion. This means that L1 is not retired yet, so we have successfully validated protection, and as a result, we get the protected assertion by upgrading the HP slot assertion. This assertion represents the permission to read L1, and importantly, it's separate from the managed assertion, so we can access the node even if it gets retired. And finally, when the thread unprotects, we downgrade the protected pointer assertion to HP slot. Now let's make our specification generally applicable. To do so, we need some mechanism to support mutation. So what I mean is that the specification we just saw doesn't support rules for writing like this. This is because the managed pointer assertion and the protected pointer assertion talk about the same memory block, which means that they must agree on the value. So we can't allow modifying just one of them. The solution is to introduce something else to be agreed upon. To this end, we replace the value with the block invariant. The block invariant serves as a logical ID that these assertions can agree on. And in addition, it describes how the memory block can be mutated. So when we have protected, then we can temporarily obtain the points to assertion of the node and mutate it as we wish, as long as we maintain the block invariant. Finally, we are ready to verify the list example. First, the invariant of the list is similar to the old one. It contains managed assertions for the non-detached nodes. Then we set up the block invariant to include the marking protocol. For L1, it says that if L1 links to L2 and is not marked, then both of L1 and L2 are not detached. Now, suppose thread 1 wants to protect L2 with slot P2. When T1 calls protect on L2, we update the slot and to validate the protection. T1 checks the link from L1 to L2 and sees that it's not marked. Then from the block invariant, we learn that L2 is not detached. And from the list invariant, we get the managed assertion out of L2. So we can upgrade IHP slot to a protected pointer assertion. On the other hand, thread 2 wants to remove L1 and L2, so it marks the links. And now the left-hand side of this implication is false. We may detach L1 and L2. So when they are detached, we can take their managed out of their list invariant. And when they're retired, we pass them as a precondition of the retire function. So that's the key idea of our hazard pointer specification that supports compositional verification while being generally applicable. We apply this style of specification to another popular reclamation library called RCU. So RCU is relatively simpler than hazard pointers. It provides the function to activate a critical section, which basically protects everything. So in a critical section, you can traverse the list without extra work. And even if some nodes are removed and retired, you can keep traversing without restarting. However, this protection only works when clients maintain some subtle additional invariants on the link structure, which can be tricky to reason about. So our specification abstracts away this reasoning. The key idea was to extend the managed pointer predicate with the pointed by parameter, and which tracks the incoming references of the node and enforces the rules about the link structure. For evaluation, we formalized and verified our specification in Cockproof Assistant with the IRIS framework. We successfully verified several lock-free data structures, which shows that our method is generally applicable. And to our knowledge, this is the first verification of these data structures under manual memory management. Also, the overhead of adding reclamation to the code was on par with the overhead of the proof, which indirectly shows that our method is indeed compositional. So that's the end of my talk, but there are some interesting details that I left out. For example, in the paper, we'll talk about how to verify the hazard pointer and RCU, and we'll discuss how to verify the clients and see what's interesting about their proof. And we also automated some client verification with diaphragm. So that's all. Thank you for listening, and I'd be happy to take any questions.
Great. Are there questions? Yes.
This looks really interesting. So in the way you're presenting invariants,
Yep.
I guess you're using the IRIS style kind of ghost state sort of protocols to deal with the individual pointers you have into the invariant. Is that?
Oh, yeah, right.
Yeah. And the other question, so hazard pointers kind of are quite interesting from a weak memory point of view. Did
Yep.
you look at that at all?
So actually, we are working on that right now. So it has some interesting properties because it uses the memory barriers for protection and validation. And it has some, interestingly, it has some global effect on the data structure. So the main challenge is that you have to model how to this memory barrier affects the the data structure invariant.
Great. I have one more question as we're switching to the next speaker. So I was curious about. So you've applied a similar technique in 2 different case studies in
Yeah,
your
right.
paper, which is really cool. Can you give us an intuition for why you? I mean, I think you're making an assertion that this is a general technique, right?
Yeah.
Can you talk about why, conceptually, why you feel it's generalizable? You know, given what's in common about these 2 case studies that might also work for in other situations?
So in fact, we have sketched some this style of sophistication for other reclamation libraries. So there are some more case study in our paper. And the reason I think this is general is that, so it basically reflects your intuition about how these pointers are protected. So if you think it's intuitively possible, then you can come up with some abstract predicates with what it means for some pointer to be protected and what it means for some threads to be in a critical section. So yeah, that's why I think it's a general approach.
Excellent. Thank you. Let's thank the speaker again.